Hello everyone. Okay, this is the part number 3 under module 11, lesson number 1. All right, so let's go. This is about aeroplane aerodynamics and flight control. So already I did 2 lessons. So this is the third lesson. So this is not the third lesson. This is the part 3 under lesson number 1. All right, so if you still not subscribed to Aviation Engineering, please subscribe. Please share these videos with your friends and relatives. All right, so okay, so now let's go to the lesson. All right, so today I'm going to do the part number 3 under module 11, lesson number 1, aeroplane aerodynamics and flight controls. All right, so let's go to the content. All right, so in the content, I'm going to explain for you guys primary control surface designs under that aerodynamic balancing. So the inset hinges and horn balance, aerodynamic balance panel, and internally balanced waistland air wing. And the mass balance under that tabs, balance tabs, anti-balance tabs, servo tabs, spring tabs, and finally control surface bias. Okay. All right, so let's go to the first one, primary control surface design. All right. Okay. Right. So every control surface on an airplane, like aileron, elevators, and rudder, is like a small wing. Okay, it's like a small wings. Right. Remember, every control surface is like a small wing, right? So these surfaces have their own center of gravity. Every control surface have its own center of gravity and center of pressure. Just remember, okay? Not only for whole aircraft, every control surface have center of gravity and also center of pressure. Now see the problem. If the control surface is hinged right at the front, it means leading edge, then all the weight behind the hinge make it hard to move. Okay, example, like if the control surface is hinged right to the fixed wing from the leading edge, then all the weight behind the hinge make it hard to move. So the pilot has to work harder to move the controls because there is no mechanical help. Okay, just imagine what I say. Okay. Right, there's a solution. So solution is balancing the control surfaces. Okay, what is the solutions? We have to balance the control surfaces. So to make it easier for the pilot, engineers use two type of balances. Engineers using two type of balancings. Number one is aerodynamic balancing, uses the airflow to reduce the control force. And the second one, the mass balancing. Mass balancing is use weight to reduce unwanted movements. Okay, just remember. So types of mass balancing. Now the types of mass balancings. So they have two mass balancing, internal mass balance and external mass balance. So the internal mass balance, like a weight is added inside the leading edge of the control surface, and the external mass balance is a weight is added outside using a small arm called a horn. Or this is useful when internal weights would make the aircraft too heavy. All right. So the external weight is smaller but placed further out. Okay, which gives the same balancing effect with the less weight. Okay, just remember. Okay, now let's go the stability and control. So for the aircraft to fly smoothly without constant input, hand off flying, the control surface must change with airspeed. Okay, so some balance must be adjustable in flight by the pilot. All right. Okay, so now what do the primary controls do? What do the primary controls do? So ailerons roll the aircraft. Okay, I discussed in the early videos. Aliens what they do, roll the aircraft, rotate around the longitudinal axis, and elevators pitch the nose up or down around the lateral axis, and the rudder yaw the nose left or right around the vertical axis, right? So auxiliary controls, to help the primary controls work better, most planes have extra small surfaces called tabs and the trailing edge of the main controls. So these tabs help the pilot by reducing the amount of force needed to move the control surfaces. All right, so now let's go to the aerodynamic balancing inset hinges. Okay, aerodynamic balancing inset hinges. So like when a pilot move the control surface, like aileron, rudder, or elevator, like manually, it can very hard to move them. Okay, when the pilots move the control surfaces manually, it's very hard to move them, especially if they are hinged right at the front leading edge. So this means the pilot must use full force to move the surface. So they have a solution. The solution is we use aerodynamic balancing. So to make it easier for the pilot to move the controls, designers use aerodynamic balancing. This means they use air pressure. Okay, they are using air pressure and airflow to help move the control surface, so the pilot doesn't have to work so hard. So what did they use? They are using air pressure and the airflow. Okay, so there are two types of there are two common types. What are the two common types? One is inset hinges and the horn balance, right? So the inset hinges, the hinge is placed slightly inside. In the inset hinges, the hinge is placed slightly inside the surface instead of right at the leading edge, and this allows part of the control surface to stick out in front of the hinge, and that front part catches the airflow and helps move the surface, reducing the pilot effects. And then the horn balance, a small part of control surface extend towards of the engines. Okay, a small part of control surface, okay, a small part of control surface extends forward of the hinge, often shaped like a horn. So when air hits the horn, it pushes it and helps turn the control surface. So this makes it lighter and easier for the pilot to move. Okay, what are these? There are two types of two common types. What are they? Inset hinges and the horn balance. Just remember it. Right, so now let's go to the inset hinges. So inset hinges are type of aerodynamic balance used to make fly easy. So what is an inset hinge? What is an inset hinge? If the hinge line, like the part where the control surface moves, is placed a little behind the leading edge. Okay, a hinge line is placed little behind the leading edge is called an inset hinge. So this means when the pilot moves the control surface, like the rudder elevator, the front part, it means the leading edge of that surface, will stick out into the wind and on the opposite side. Okay, if the control surface like move, if it is move up, the in the front parts little bit go down like this. Okay, so what happens then? When the leading edge moves into the airflow wind, the air pushes on it. When the leading edge like this, the air pushes on it, creating a force. So this force helps the pilot to make the controller easier to move. Okay, so why is this good? So it means the pilot doesn't have to use as much strength to move the controls. The air helps to do this job. All right. Okay, so simple example, think of small fin sticking out into the wind. So this wind hits it and helps turn the whole surface. So that's how inset hinges work, using wind to help the pilot. Okay, you can see the inset hinge. Okay, here is the hinge location, here, here. Okay, these are the hinge location. All right. All right, so these are the inset hinges on DC-3, inset hinges on the DC-3 aircraft. Okay, here inset hinges over there, right? All right, now let's go to the horn balance. So a horn balance is a smart design feature used on the control surface like a rudder or elevator to make fly easier for the pilot. So what is an horn balance? What is horn balance? So it's a small part of control surface. It's also a small part of control surface that stick out, it's come out, protrudes in front of the hinge line. Okay, it's come out from the front of the hinge line. So it's usually placed at the side outboard edge of the rudder or elevator. So when the control surface moves, when the control surface is moved, the air hits on the horn, helps the surface move easily. Okay, just imagine. So how does it help? So the horn catches the wind and creates a force that helps the pilot move the control surface. So this is called aerodynamic balancing. Okay, so the horn is placed in front of the hinge, so the air pushes it in the same direction as the pilot is trying to move. So double benefits, aerodynamic plus mass balance. Since the horn is in front of the hinge line, we can place a balance weight on it, right? So because a horn is far from the hinge, the small weight has a strong effect due to the long arm. So the horn also works as a mass balance, reducing unwanted vibrations or flutter. Okay, they have two kinds of benefits when we use the horn balance. Okay, yeah, so this is called the horn balance, protrudes out of the control surface. Okay, this is, you can see horn balance elevate on specify on split fire. Okay, here is the horn balance. Okay, this is the hinge line, this is the horn balance. Okay, horn balance schematic. Right. Yeah, you can see the horn balance, rudder, airstream. This is the horn balance. Okay, right. Okay, now let's go to the aerodynamic balance panel. So aerodynamic balance panels are special device used to make aileron easier to move. Aerodynamic balance panels is a special device used to make aileron easier to move, especially at high deflections when the pilot moves them a lot. Okay, so problems and the basic balances. So simple aerodynamic balance like horns do not increase their health as the pilot move the control surface more. Okay, so but when the pilot moves the surface more, they need more help. Okay, if the pilot surface they need more, they need I mean, if the pilot move the control surface more, then they need more help, not less. Okay, so the solution for this one, aerodynamic balancing panel, they are using aerodynamic balancing panel. So an aerodynamic balance panel gives more help as the control surface is deflected more. This means small movement they will give small help, and also large movement they will give more help. Okay, so how does it work? A balance panel is placed inside the wing structure. A balance panel is placed inside the wing structure just in front of the aileron. Okay, and this panel is hinged. Okay, this panel is hinged, lightweight, and divides the space in front of the ailerons into two air compartments, right? So one connects to the top gap between the wing and aileron, and the second one connects to the bottom gap. Okay, right. Okay, you can see, right? Is connected to the top area, and the second, okay, and the second one connect to the bottom gap. One connect to the top gap, and second one connect to the bottom gap. Okay, right. Yeah, so what happens when the aileron moves? What happens if the ailerons moves? Ailerons moves up, air flows faster under the wing, create a low pressure in the lower compartment. Okay, air flows under the wing, creating a low pressure in the lower compartment. And this low pressure pulls the balance panel down. This low pressure, because of the low pressure, is push the balance panel down. So that pull on the front of the ailerons helps lift the back of the ailerons up. So the panel assists the pilot in moving the aileron. Okay, so when the ailerons moves down, the same thing happen in reverse. When it go up also, the same scenario happens. So to move, you move, the more it helps. Okay, the more you the more you move, the more it helps. Okay, so the greater the deflections, the more pressure difference. It means if there's a greater deflections, then they have more pressure difference, and the stronger the helping force. This is why it's very effective at high speed or during strong control movements. Okay, yeah, you can see the balance panels. Here is the hinge, and this is the balance panel here, and the air moves from here, right? This is the vent gap, and this is the low pressure area. Okay, this is the control tap and vent gap. Okay, right, just go through this picture and just understand what I said in before, right? Okay, now let's go to the internally balanced Westland air wings. Okay, internally balanced. Okay, just look at this picture, right? So the Westland air wing control surfaces uses a special internal aerodynamic balancing method to make the control surface easier to move. Okay, so how does it work? It has a rubberized fabric seal between the leading edge of the control surface. Here is the rubberized seal, leading edge of the control surface, and the main part of the wing aerofoil. Okay, this is the main part of the wing aerofoil, and the leading edge of the control surface, they have a rubber seal. So this design create an airtight seal, so air doesn't leak through the gap. So why is that helpful? So this seals gives a large effective area in front of the hinge line. So that means more air pressure built up in front of the hinge when the surface moves. Okay. So the air pressure helps push the surface. So the pilot doesn't have to use much more force. So also because air doesn't escape, there's a less pressure loss, which make the balancing more effective. Okay. So adjustable louvers, extra control. Sometimes the system include adjustable louvers like small flaps in front of the hinges. So this allows some of the air pressure in front of the hinge to bleed off, escape. Okay, so this helps the engineers or technicians to adjust how much balancing force is applied. So example, like if too much balancing force is making the control feel too tight, too light, the louvers can release pressure so to reduce the effects. All right. Okay, now let's go to the mass balance. Mass balance. So some aircraft control surfaces like aileron, elevators, or rudder can suffer from dangerous problem called flutter. It's getting flutter like this when it's because of vibrations or something is getting flutter. A fast and uncontrolled vibrations or oscillator around the hinge line. Okay, so this is very big problem. So what is flutter? Flutter is when a control surface shakes or vibrates very fast. It can happen at high speed and many damage to the aircraft if not fixed. Okay, to prevent flutter, engineers use something called mass balancing. Okay, to prevent flutters, engineers use mass balancing. Okay, what is mass balancing? Now let's know what is mass balancing. Mass balancing means adding weights to the control surface to make sure it's balanced around its hinged axis. Okay, so the goal is for the center of gravity of the control surface to be right on the control surface to be right on the hinge line, and this stops flutter because the surface doesn't want to swing or vibrate freely. Okay, what is why we use mass balancing? To prevent flutter oscillations when it's flying. Okay, right. So how is it done? Right, usually weight is added in front of the hinge line. Usually what is they doing, they add the weight in front of the hinge line, and this weight is called the mass balance weight, and it cancel out the weight of the materials behind the hinge, so the surface is balanced. So after repair, why recheck mass balance? If repair is made to the control surface, it often add extra weight. Okay, if the weight is not exactly at the center of gravity, it will move the balance point. So after the repair, the mass balance must be checked and possibly corrected. Okay, how is the mass balance checked? The control surface is removed and placed on the special fixture that let it move freely. Then technicians then let the surface swing freely, adjust the balance weight until it sits in the correct position. So sometimes a graph or chart is used to calculate how much weight and to add or move based on the distance from the hinge line. Okay, so important points like mass balance is important for all control surfaces, even if they are boosted like with hydraulics, right? It must be done very precisely, okay, because the results directly affect safety of the aircraft. Okay, right. So these are called the mass balance. Okay, just put some balance in front of the leading edge of the control surface, balancing weight and external mass balance. Here is the auxiliary mass they put inside in front of the control surfaces. Okay, right, now let's go to the tabs. Tabs are small control surfaces attached to the trailing edge. Okay, tabs are small control surfaces attached to the trailing edge of the larger flying control surfaces like ailerons, elevators, and rudder. Okay, tabs. So what are tabs? Tabs look like mini aerofoils. Okay, tabs also look like a mini aerofoil. Are shaped like a main control surface. It's also shaped like a main control surface. They are hinged so they can move up and down. So when a tab moves, if it uses the airflow to create a force that helps or change the environment of the main control surface. So why are tabs used? Tabs are developed as aircraft. Tabs are developed as aircraft evolved from manual to power assisted control. They help the pilot control the aircraft more easily, accurately, and safely. So there are 5 types of tabs. What are they? Trim tabs, balance tabs, servo tabs, spring tabs, and anti-balance tabs. So trim tabs keep the aircraft flying level without the pilot needing to hold the controls all the time. And balance tabs helps move the main control surfaces with less effort. Balance tab we talk. And servo tabs move first. Servo tabs is move first, and then it moves the main control surfaces. Servo tab it's move first, and then it control the control surface used in big or power assisted aircraft. And spring tabs works like a servo tab, but only helps when the pilot input force increases at high speed. And anti-balance tabs work in the same directions as the main control surface to make it harder to move, giving the pilot more control feel. Right, how do the tabs work? Most tabs are designed so that when they move in one direction, they push the main surface in the opposite directions. Okay, remember tabs always move in the opposite directions. It means when the control surface move to right, and the tabs move to left. Okay, example, if the tab moves up, the elevator moves down. Okay, okay, if the tabs moves up, elevator moves down. Okay, and aircraft nose goes up. Okay, just remember. Extra info: one control surface like an elevator may have multiple tabs, or one tabs that does more than one job. Okay, so the mechanical linkage, how it's connect it, what makes each type of tabs work differently. All right. Okay, these are the types of trim tabs. You can see control column horn Here is the tab, okay, and this is the trim tab and the servo tab. Here the horn free to pivot on the hinge axis. Here servo tab, here is the tab, okay, and the balance tab, here is the balance tab, and the spring tab, okay. This is, there's a spring, like a spring cartridge is there, okay. The trim tabs over here, right, you can see. Now let's go to adjustable tabs. Adjustable tabs are small surfaces on the back of the non-powered control surfaces, like manually control elevator or ladder. Okay, so adjustable tabs are small control surfaces on the back of non-powered control surface. They are used to fix small flying problems, such as aircraft that always pulls to one side or pitches nose down. Adjustable tabs. So who adjust it? Only ground crew or maintenance staff can adjust it. Okay, only ground crew or maintenance staff can adjust it. So the pilot cannot change it during the flight. So it adjusted on the ground before or after flight based on the pilot's report. Okay, so how it is adjusted? There are two type of adjustable tabs. A real tab moves removing a plate, positioning the tab, then tightening it back, and the metal strip simply bend into the new positions using a special tool. Okay, so how does it work? The tab is moved in opposite directions to how you want to control surface to move. Example, if the aircraft always pitches nose down, then the elevator needs to move up, so the tab is bent downward to push the elevator up using the airflow. Okay, that is called adjustable tabs. Remember, the key points is adjustable tab. You can change only in the ground. Okay, pilots cannot change the position. And now the trial and error. This adjustment is not exactly. The tab might need to be readjusted after the next flight depending on what the pilot reports. Okay, so ground adjustable trim tabs here. Okay, you can see it's hinge right here, these kind of things. Right, now let's go to the controllable tabs. Controllable tabs are small surface attached to the back of the non-powered control surface, like elevator or rudder. But unlike adjustable tabs, the pilot can control them from the cockpit during flight. Okay, adjustable tabs cannot control by the pilot but during flight, but the controllable tabs pilot can control during flight. So what are they used for? The pilot uses them to correct flight errors while flying, and they help keep the aircraft flying straight and level, and they can also be used to help the aircraft climb or descend without the pilot holding pressure on the control stick. Okay, how do they work? The tab is connected to the control in the cockpit. It can be moved by cables, chains, screw jacks, or even an electric motor, electric actuator controlled by switch on knob in the cockpit. Okay, so where are they used? These tabs are fitted on non-powered control surfaces. They allow the pilot to make fine adjustment in flight, like trimming the aircraft. Okay, you can see okay, you can see the trim tab here is controllable. Okay, cable operator screw jack here, trim control caps. Okay, you can see this is also controllable tabs, right? So example, if the aircraft tend to pitch up, the pilot can move the elevator tab up, which makes the elevator move down, correcting the pitch. All right. Okay, now let's go to the balance tab. So balance tabs are small helper surface attached to the trailing edge of the main control surface, like an elevator or rudder. Okay, balance tab. So how do they work? The balance tab is connected to the main control surface by a adjustable rod. Remember, balance tab is connected to the main control surface by an adjustable rod. So the rod is attached to the fixed part of the wing aerofoil, wing or airfoil, and when the pilot moves the main control surface, the balance tab moves in the opposite directions. Okay, when the pilot move the control surface, like let's example, if they move to the right, then the balance tab move to the left, opposite directions, but at the related angle. Okay, so why is this helpful? The balance tab creates an aerodynamic force. Wing pushes on it. Although this force is small, the tab is located far from the hinge line. So because of this distance called the lever arm, the small force creates a strong turning movement, right? This movement helps the pilot move control surface more easily. Okay, so adjusting the tab, the amount the balance tab moves can be changed by moving where the rod attached. Okay, moving the connection point closer or further from the hinge changes how much the tab moves compared to the main surface. Okay. All right, here is the balance tab. You can see, right? Tab geared to the defect proportionally to the control deflections, but in the opposite direction. Okay, here control surface moves down and the tab moves up. Okay, because of that, this one have more feel. Okay, right. Now let's go to the anti-balance tab. So anti-balance tab is used to make the control surface more responsive. Okay, anti-balance tab is used to make the control surface more responsive and give the pilot better control feel. How does it work? It looks like a balance tab, but the linkage is different. The anti-balance tab moves in the same directions as the main control surface, but it moves even more than the main surface. Remember, the balance tab, it's move opposite directions to the control surface, but the anti-balance tab, it's moves the same directions as the control surface, but is move more than main surface. Okay, so what does it do? This makes the control surface more effective and more sensitive. It changes the shape of the control surface. It changes the shape of the control surface by giving its curved mean chamber line, improving how well it is move air. Well, it move air. Okay, so why use it? Why we use it? The pilot feels more connected to the aircraft. The control surface responds faster and more precisely. Okay, right. You can see the anti-balance tab. Okay, here anti-balance tab, it move the same directions. Okay, so you can see this control surface if moved to the this up, then anti-balance tab is move up also, but in more it's move more angle than the control surface. Okay, right. Anti-balance tab schematic. Right, now let's go to the servo tabs. A servo tabs look like a balance tab but works in a different way. Okay, servo tab also look like a balance tab but is working in a different way. How is connected? Instead of the pilot moving the main control surface directly, the pilot move the servo tabs first. Okay, in the balance tab and anti-balance tab, the pilot move the control surface. According to the control surface, the balance tab or anti-balance tab moves. But in servo tabs, the pilot move the servo tab first. Okay, the pilot moves the servo tab first. The pilot controls wheels or pedals connect directly to the servo tab, not big control surface. Okay, so how does it work? The servo tab is at the trailing edge of the control surface, and when the pilot moves the servo tab up, the air pushes on it. This aerodynamic force then moves the big control surface down. Okay, this is very good. All right, so if the tap surface move down, it causes the main control surface moves up. Okay, in servo tab also, the control surface moves opposite directions to the servo tab, but the difference is in the control tab, servo tab, pilot moves the servo tab, not the main surface, right? Okay, so if the control surface moves until the force on the tab, the surface balance out. Okay, right. So why use servo tabs? They reduce the effort the pilot needs to move the large control surface. Okay, because why the servo tab? Now the pilot needs to move only the servo tab, not the big control surface. So the pilot effort is less, especially on planes without powered controls, and they help pilot control the aircraft more easily. Okay, you can see the servo tab here, the pilot's control stick. The pilot move the servo tab. According to servo tab, the main control surface is moving. Okay, right. Now the spring tabs at high airspeeds, it becomes much harder for at high airspeed. It becomes much harder for the pilot to move the control surface because of the strong air pressure. So why is a spring tab? A spring tab is a similar to servo tab. Spring tab also similar to servo tab, but it works only when the airspeed increases. Okay, remember, uh, the spring tab also same like servo tab, but its work only in high speeds, right? Airspeed increases. At low speed, the pilot move the control surface directly as usual. Okay, in the low speed, the pilot move the control surface as usual, but when the airspeed is increases, at this point the spring tab is activating. Right, so how does it work? The control surface and the tab are connected by the torsion bar, a type of spring. At low speed, the air pressure is weak and can't overcome the spring, so the pilot moves both the control surface and the tab together. At high speed, air pressure resists the control surface movements. The pilot force overcomes the spring, moving only the tab. So now the tab acts like a servo tab. It uses air pressure to move the big control surface. Okay? Right, so why use spring tabs? They help reduce pilot effort. When flying fast, at low speeds, the pilot has full direct control. At high speed, the spring tabs helps move the control surface safety. Okay, you can see here is the spring, same like the servo tab, but it works only the airspeed is at high. Okay, right, high airspeed only this uses. All right, this is the free link and control stick. Okay, now let's go to the control surface bias. Okay, that is the end. Control surface bias. A control surface bias means the control surface is not exactly at the neutral or center positions when the control surface are neutral. Okay, that is called surface bias. So why does bias happen? Sometimes design features or forces on the aircraft causes to naturally pull or roll in one direction. For example, a single engine propeller aircraft might tend to roll due to the engine's torque turning force. Okay, we discussed previous lesson. So how is bias used? To fix this, the control surface like ailerons are set with the bias. So one ailerons might be slightly up and other slightly down when the controls are at neutral. So this helps counteract the rolling force caused by the engine torque. Okay. So what happens next? When the aircraft flies level with the bias, the pilot adjusts the trim gauge to 0. So this means the aircraft stays straight and level without the pilot needing to hold pressure on the control. All right. Okay, that is the end of part number 3 and lesson number 1. All right, so we have 2 more parts to finish lesson number 1. All right, so if you still not watched the previous lessons, please watch these lessons. Yeah, I think my recommendation is better you watch the previous 2 lessons and come to this lesson. Okay, then this one have a flaw because that's why I put a playlist. All right, so if you still not subscribed Aviation Engineering, please subscribe again, and this will make me more energy to make new videos for you guys. All right, and I like more community will engage with my Kwiation engineering YouTube channel, so it will help for more people to get knowledge. All right, so and if you have any questions, anything, just comment below and I will respond as soon as possible. All right, so again, thank you very much for participating in this lesson and see you on next lesson. Have a great day for all of you.